Today I'm going to be showing you how I made this infinite rainbow tunnel entirely in Blender shader nodes. So first thing, I just have to admit that I ripped this off from an exponentially more elegant shader on shader toy. So there's a link to that in the description if you'd like to actually see the code that I was basing this off of. But let's jump right into it with that off of my chest. We have our new default file here. And we're just going to go ahead and make sure, go to Edit Preferences, and make sure that you have your GPUs turned on if you have any of them, and make sure that we're in cycles, because we're going to be doing quite a bit of math today, and we don't want to put that all on your poor CPU. I mean, maybe the CPU could handle it, I don't know, I haven't tried. And so you can go ahead and delete your principled, and just to make things clearer, you can turn scene lights and scene world on, and you can even delete your light. And what you should have is this black box, which is all ready for Raymarching, because that is how we're going to be making the effect today. So if you've never Raymarched in Blender, it's actually super easy. And if you don't know what Raymarching is, that's okay too. It's pretty easy too. The kind of basic rundown of what we're going to be doing is we have some sort of observer, an eyeball, or a retina, a camera, something. And this is our ray origin, okay? And we are going to shoot a ray out from that according to a ray direction and a ray distance. Okay, my tablet's not working, so I'm using my mouse. So that's the three main attributes of the Raymarching function, and with these three attributes, you can basically take Blender's infinite coordinate space that it has inside of itself, and you can calculate using this distance function any sort of 3D shape inside of that texture space. And the resolution of it is basically iterative. So it's called Raymarching because we march out the ray iteratively and see if it hit something, yes or no. And if it did hit something, then we march again. And eventually you start to see the depth of the shape in the field, whatever it might be, you know, some spheres or something. For our case, it's going to be this tunnel. But the resolution of this is dependent on the iteration count. It has nothing to actually do with pixels, so to speak, or like any sort of ray count or anything. And so that's going to make more sense in a second. Excuse me. So we need our RO, our ray origin, and we need our ray distance, and we need a distance function. So actually, if you pull up your geometry node, you can get two of those coordinates right off the bat. Our position is going to be our ray O. So basically what we're doing is we're saying for our cube here, every face of the mesh is actually, we're treating it like an eyeball or a camera. It's casting the ray out from that point. That's the origin. And then our incoming, which, in case you didn't know, tells you it tells you the direction that the face is facing towards the camera, if that makes sense. That incoming is going to be our ray direction, because if you imagine you're casting a ray out orthogonally from your eyeball, and the eyeball is our camera in this case, the vector that points from the face to the camera would be the direction of the ray of light. So RO is our position and our D is our incoming. And so the way that you Raymarch is you scale your incoming by a distance function. So what this basically means is you're sending a ray of light out from your eyeball, and you're saying, only send the ray out this far, and when it gets this far, when it gets that far, what we're going to do is move the position of our mesh by vector subtract according to that ray distance, the scaled ray distance. And so where we get the distance function from is from our shape. So we can just quick do the first easy Raymarch example, which is take the length of your position vector math length, and this length is telling you its proximity to 0, 0, 0, the absolute origin center of the world, right? So what you get is a sphere. And it's hard to see that it's a sphere with the UV when it's showing you the actual position coordinates of it. But if we take the length again of this final vector, you'll see that it gives us a sphere. And this sphere is infinitely resolute. Well, it's infinitely resolute to the degree that you can iterate. And so what are we iterating? Well, we can take this final length away. You don't need it. It's basically just for visualization's sake. Take the length, the scale, and the subtract. Go ahead and Control G. And we can name this our Raymarch group. Okay, so I'm just going to clean it up. I want my position to be at the top and my incoming to be at the bottom. Okay, and I'm going to clean this up. I want the top attribute, this is our RO, to be fed into the subtraction, and then our bottom attribute gets scaled, and the top attribute needs to be plugged into the length. So it should be set up like this. So this is our RO, and this is our RD. So I just had to fix everything up because everything got all janky, but just to go over this again, you subtract your scaled ray direction, which is scaled by the distance function, from your ray origin, which is the position of the mesh, and what this gives you is your first march. It tells you where the rays have landed or not, and it starts to render out a 3D shape. So what you're going to want to do next is just go ahead and take your RD and feed it all the way through to the other end of the group output, and name these the same exact thing on the other side. Top one is RO, bottom one is RD. And this is your iteration group. So we didn't come here to make a sphere necessarily, we came here to make a crazy tunnel. So we'll start with the floor, since that's easy. And what we're going to be doing is making one of these entire setups again. So, but instead this time, we're going to take our ray origin, RO, and we're going to separate XYZ. And if you want to view this, you can Control-Shift-Click to view, and just go ahead and go to the Z axis. This is already basically our distance function for the plane. So we just need to go out of here, or no, go back in, sorry. We need to subtract RO and RD, a scaled RD, except we can't use the same one. And I'll tell you why in a second. It's because we're going to use this one for the walls of the tunnel, and this one is going to be the floor of the tunnel, and they actually take in different positions. And the reason for that will become evident, even though it's maybe confusing right now. So I'm just going to pull from this subtract node and add a new node into our group. And then I'm going to take our position and I'm going to put it there. And like I said, they need to be separated for a reason. And what we can do is call this vector plane position. Okay? And so we're subtracting our plane position, our scaled RD from our plane position. So we need to scale RD. And what we're going to be scaling it by is this Z axis. But we have to add a little bit. We have to add like 0.06 or something like this. And then this, we're going to, I have a viewer node, so just pretend that If you use the viewer, you'll have a viewer node too, and it'll disappear, so just don't touch it. Plug into your output this plane position minus the scaled RD, scaled by the distance function of the plane, goes into this bottom one, and this is our plane position output. Okay. So if we view this, it's not exactly right. I forgot we need to clamp it. And then we can just go ahead and add another iteration, or 2 or 3. The more you add, the clearer the Raymarch gets, but the more you add, the more computations you're doing. And then from our RO slot, just go ahead and add in an image texture. And we're going to go to New, Color Grid, New Image. And now we can actually see what's going on. And it's not working like we want it. So because we need to be putting our plane position into there to see the plane. So as you can see, it is Raymarching out the plane. And you just want to double check and make sure that your plane position is what's plugged into the separate XYZ. And there is the plane. It does render a little weird. It does the thing where it like recedes up to the horizon, but I don't know how to fix that, and it'll go away once we do the rest of this. So these 4 nodes down here, this is our plane distance function. Okay. And so then up here, we have our sphere that we made earlier. And so we're going to turn this into our walls. And this is actually super easy. What we're going to do is we're going to take our RO, our ray origin, and we're going to subtract, vector subtract. From this vector subtract, you can just add a value. It's a float value. We're subtracting 0.5, and then we're going to take a fraction of this. And what this is going to do is return only the 0.5 that we added. And then we're going to vector subtract from this same float value, 0.5, which I think puts everything back where it's supposed to be. Then we're going to take the length of this and we are going to subtract this length from 0.68. And so basically what that's doing is we're taking our RO, which is the plane, just the plane cube as it comes. We're moving it, we're nudging it 0.5. We're taking only the 0.5 remainder. We're nudging it back into place. And then we're taking the length of that, which gives you a bunch of circles that are spheres like you would expect, like our sphere we made in the beginning. And then we're subtracting that sphere from 0.68, which gives us the walls of the tunnel. And so this will be our distance function. You can delete the length from the beginning, and you can just plug this into the scale. And it is starting to work. But one last thing is fucked up. We don't want our original RO. You want to come over here right before the length at the subtract node. This is our new RO. So basically, when we're doing this fraction operation, that is your new RO vector. And so you're going to scale your ray direction by this distance function and subtract the fractionated, not a word, I know, I don't care, the sort of, tiled one instead of the original one. And make sure that's plugged into your RO. And then we can go ahead and put that into our UV map or UV grid. And you can see it's already starting to happen up here. So you can adjust this value if you want, but about 0.68 is what looks good. And it only has a few iterations right now, so it doesn't look super crisp. So next thing we're going to do, we're basically almost done. We're just going to combine the distance functions so that our RO reflects this. So instead of just scaling this directly, which let's name this all. This is our walls SDF. We're going to take the minimum of our two distance functions. So just regular math minimum, since they're both floats, and just take those both and keep them plugged into the scale still on this bottom one. But on this top one, just plug them both in. And now you can come down here to your add, and you can adjust the placement of your floor. You can put it basically in the middle, wherever you want it. And we're almost done with the main part, and then we'll add in lights and stuff if you want to stick around and do all that. We just need to basically add a jillion more iterations and we're Gucci. So I'm just gonna do that real quick. And just make sure that your RO is plugged in to the vector slot. And look at that. We're basically done. Okay, so what you'll notice is the first big artifact with Raymarching Blender is that you're clipping through the side of your mesh. And so the way to kind of subvert that in this scenario is that we're just going to go up here to object mode. Just go ahead and bevel your mesh all the way to hell and back. Go ahead and click clamp overlap and add in a reasonable amount of segments. Be kind to your computer depending on its abilities, right? And even that's pretty low poly, but that is enough. You can go over here to view and just lock your camera to the object. Zoom all the way in, and you'll notice we're basically inside of the thing, but it's still clipping the inside of the mesh. And the way to fix that is super easy. You just need to scale your sphere down until it's smaller than the walls. And then you won't clip into the floor, you won't clip into the walls. And you can just explore around in here. If you want to navigate through, you're going to vector add to the RO. And then if you move that, you can move through the tunnel. You can move literally any direction you want. But if you want to fly, then you need to also plug that into your plane position. And then they'll both respond. Although it's a bit glitchy if you try to fly. So I don't know. If you're smarter than me, you can figure out how to fix that. But we're already at 20 minutes and we still don't have any lighting in this mesh. So let's just finish up that last thing. and you'll be good to go. So the lighting isn't actually that complicated. This looks super duper messy. What we're going to be basically doing is one more iteration of this Raymarch loop, but we need a light. And so what you're going to do is go up here to add, go up here to empty, and add in an empty plane axis. And you can change it to basically whatever you want. I like to use the arrows because they're kind of big. I can grab onto them. So I don't think this needs to be quite that small. Actually, we're still not clipping through the floor. No, we are. There we go. Okay. So I have this plane axis. So what I'm going to do is add in a texture coordinate node. And we can rename this to light to just be clearer. And make sure that you pick your light object, the empty, in your texture coordinate. And then go ahead and duplicate your Raymarch group. And plug in the RO. Plug in the plane position. And then your RD, our ray direction, is actually going to be the object information from the axes. So basically we're taking our light direction and we're marching a ray in the light direction instead of marching it from the camera direction. And so the light direction is going to tell us whether or not something gets hit by the light or not, as opposed to telling us whether or not we see it or not to render it, if that makes sense. So we're basically just kind of like cheating in a way. So you're going to have to iterate it a few times. We'll try like 4. The more times you iterate it, the cleaner your shadows are going to look, which is pretty intuitive. And then we just have to append one more thing to this. So I'm going to go ahead and get rid of the viewer thing because it's still there for some reason. And where we took our minimum, you just want to also bring that over to your group output. And what you're going to call that is your distance function. You can call it dist. And if we look at this from our viewer node, if we look at this in terms of this, we can take our light and we can move it around, and you can see it tells us the information of where the light is hitting, which produces basically the effect of cast shadows. So now you have a light inside of your scene and you can use it to make lighting masks and stuff. But if you look at it closely, you'll notice one thing is that it only works, it doesn't entirely work on all of the surfaces. So what you have to also do is one more step. So we can call this, we can group all that together. And we can just call that our light group or our shadow group. Yeah, we'll call it the light group to be positive. And then if we come down a little more, we can make our normal group, which is not entirely dissimilar from this. What we're going to be doing is we're going to be basically moving the vector along this value epsilon. So go ahead and bring up a value node, call it epsilon. And it just needs to be like a tiny value. And what we're going to do is take our RO from our last step in the iteration chain, not the light chain, but the actual Raymarching group. And we're going to vector add, and what we're going to add is this epsilon. So take the epsilon and pull from it a combine XYZ, and go ahead and duplicate that twice. And on the top, it'll be the X. On the bottom, it'll be the Y. Or, X, Y, Z. It goes like that. And then what we're going to do is add it to our RO. And we're going to do this 3 times for the X, for the Y, and for the Z. So that basically moves our vector along our Raymarch mesh, so to speak, along this epsilon. And then what we're going to do is go ahead and shift D some Raymarch groups over here. And we're going to pretend that this is our new ray origin. And so take your RD from the last node group, and we'll use this RD for all of these. And it's the same thing for the X, Y, and Z. They're all the same. I'm just starting to get a little spaghettified with these nodes, so sorry about that. And finally, connect the plane position from your last output, your last node in the node network. Okay. And then we're going to take this distance function and we're going to subtract the last distance function before it. So it's basically telling us how far did the ray get along in that vector, which when we combine these all into a combined XYZ will give us a normal. So just take that last one, combine XYZ, and it goes X, Y, and Z. Super straightforward. And then if we view this, we just have to do 2 more steps. We have to normalize this vector. No shame in this vector, normalize it. It's perfectly normal. And then we are going to scale it by -1. And so it looks like it's working. It looks like it's telling us the normal direction of each face. And if we change our epsilon value to a larger value, you see you're getting less accurate normals. If you change it down to a little itty bitty tiny value, you start to get like fidelity on the corners and different things, because it's really calculating a higher resolution of normal information. Okay, and so that spits out a normal. We can realistically just throw all of this into a group because it looks super ugly just hanging out here. And we'll just call this our normal group. And so what we want is we want the dot product of our normal and our light position, which is the object information from the texture coordinate with the empty in it. Okay? And so what that tells us is, which direction of the normal are facing the light. Wherever the light touches is our kingdom, Simba. And you can see this is equally as broken as the last one. So basically all I could think to do was to just add them together and hope that they basically cancel out each other's flaws. And for the most part, if I can orient myself inside of this damn thing, that mostly works like that. You mostly get good cast shadows in reference to wherever the light is supposed to be. If we move the light a little bit, yeah, we can see it's definitely responding in a way that you'd expect, I think. Let's see, if we move it to the right, we should expect the shadows. Yeah. So it mostly works it's just dependent on, first of all, how many iterations you're doing inside of here. So like our light group only has 4 iterations. If I added some more, the light fidelity would be a lot cleaner. And then our normal group actually, I think, also is depending on this because it's marching out rays. We have a ray march going on inside of there. So maybe, I don't know. I'm sure there's different ways to make it a little more high fidelity and to fuck around with the lights to make it work. But basically, I would say just if you want to use them, you can use this as the factor in a mix and just mix go ahead and mix your checkerboard or whatever kind of tiling pattern that you want to use with black or whatever shadow color you want. And it's not working. You may have to multiply. Yeah. There you go. So that's basically it. That is how you gain access to this super cool hidden liminal tunnel space. You can just chill out in here. You can contemplate platonic space in here, smoke weed, do whatever. You can just chill. But the longer you wait in here, the more you risk running into entities, so I wouldn't risk it. That might really fuck up your computer. So, yeah, that's essentially it. There's not too much you can do to customize it, besides this could be whatever you want. You know, if you just had, say, a checker texture, you could easily just have that as your final color. Or anything. If you have a repeating texture, it'll work. But up here on these columns, you will notice that things get distorted. So you can't really have text or anything like that. And like if you saw in the checkers, it was taking from the position value to place these. And so if you get these sort of like diagonal orthogonal views of a cross section of a checkerboard, it looks like triangles, which is why they look like that. But if you're smarter than me and willing to put in the meditation on this, you know, you could figure out how to make it really cool. So I hope you at least learned something, and keep building, keep blending.